Okay, so the Fourier transformation equation is going to look like this, and we also got to know how the spectrum will look like when you take a single tone signal, modulating signal. Okay, so this is how the frequency domain representation looks like. So further to it, we can go ahead with the definition of modulation index in a much more detailed way. Okay, so when you have a multi-tone signal, it may look, more complex than a single tone. The waveform that we saw here is for a single tone case. So this waveform, what we've written is a single tone case waveform. So how will this waveform that we wrote here, where is it? Yeah. So this waveform is basically for a single tone case. If you see the envelope, that's a sine wave. So when you have a complex signal, the waveform may look maybe something like this. And you can see the carrier wave filled in within this. So the envelope is no more a sine wave, even though it is looking like a sine, but it will not be a sine wave because it's a combination of many tones as such. So it will become a complex signal for us. So in such cases, how do you basically define what is called a modulation index, or it's also called the depth of the modulation. Okay, that is defined as A max minus A min divided by A max plus A min. Let me tell you what is the meaning of A max and A min here. Okay, so when you consider a multi-tone, maybe it may look like this. Just for example, I'm writing it, and you can see the amplitudes of the carrier getting varied in accordance with the amplitude of the modulating signal. So A max is basically this part. And what is A min? If you try to see what is the minimum voltage value, this becomes the minimum voltage value. So this is A max and that is A min. So you have to find those two values and try to find what is modulation index. Okay, that is how you do it. So based on this modulation index, or which is also called the depth of modulation, okay, so we can define three different varieties of amplitude modulation. Number one, under modulation, if the value of MA is lesser than 1, and critical modulation if the value of MA is equal to 1, and over modulation if the value of MA is greater than 1. So this is what you get as. We'll see how the waveform will look like now. If you see the waveform, these are the three waveforms that we have written for three different cases. And can somebody tell me in which case you see the envelope getting retained without any sort of distortion in the envelope? Obviously it is in the first case, because if you see the critical and over modulation, you can observe this part of the wave. Okay, just a second. You can observe this part of the wave. Yeah, this part of the wave is all kind of distorted. But in case of under modulation, the wave shape is retained as it is. So that is when we say that under modulation is always good for the reproduction of the signal back at the receiver side. So we always perform under modulation. That's the meaning of this. So moving on to the next one. What are the two different methods of generation of AM? So we have gotten to know what is the definition of amplitude modulation, and how the waveform will look like, what is the time domain, what is the frequency domain representation, and we also understood the definition of modulation index and how is it going to affect the different varieties of AM, like under, critical and over modulation. So that MA value will affect the type of modulation, AM modulation we do. So after this, we have to understand how we can generate it practically. So there are two, methods of generation. One is called a square law modulator. Other one is called a switching modulator. In both these cases, we use basically a non-linear device, which will be a kind of diode. Okay. So this is the basically the the circuit diagram of a non-linear device, and the bandpass filter connection, which is basically a square law modulator. So if we have to basically understand the operation of this, if you have to understand the basic operation of this, we'll have to write few equations of a non-linear device. We'll see what is it. Okay, and probably we have that equation here. If you can observe, this is the equation of the non-linear device right here. This is basically the equation of the non-linear device. So this is the equation that we have got for the non-linear device.